Definitely need to mute my other monitor. I got a lot out of that, Mark. Got a lot out of that. Someday I'm going to actually know what a stack is after I hear him talk about it like 30 times. Doubtful. Rip. Yeah, it's probably true. Stacks seem very obscure to me. But it's probably because I don't really deal with schemes even that much, and adding structure makes it harder. I do plan on learning more category theory this summer, since I should have some time, and it intrigues me. Can you explain what a Coxeter group is? I think so. You just wanted like a yes or no answer on that, right? You should go through, you should start your defense with just all equivalent definitions of a Coxeter group, and then end your thesis by saying the rest is left to the audience as an exercise. Also, I hope your advisor is able to use Zoom for your thesis. The end of whatever you just said, but I heard enough to know it's entire. Yeah, that sounds about right. Which book are you guys using for combinatorics? I was helping someone with combinatorics yesterday, and there was a really challenging problem. I figured out the proof, except for then I found out you guys were supposed to do it by induction, and then I didn't know how to do it by induction. I don't love combinatorics. I like combinatorial things. Okay, yeah. In all seriousness, I do have some questions about your defense. Yeah, I can do that, for sure. I can do that after class. No time like 2 years after to ask questions about my defense. Yeah, that combinatorics problem was really interesting. It was like how many of these objects have exactly m of R properties. That one. It was interesting. I feel like I can always see why things should be true there, but then like coming up with the right way of expressing it in terms of factorials, or like coming out with like the binomial theorem applying to this is always challenging. And so if I'm like out of practice, combinatorics seems really hard. Alright, it seems like we have most people here now, so let's go ahead and talk more about algebra instead of combinatorics, even though it is cool. Okay, so last time, right, we had our big theorem. We had Lagrange's theorem. And, you know, as stated in the book, I mean, I introduced index a little bit after, but in the proof we basically used it. So in class, I defined index there. And so the theorem, right, is if H is a subgroup of G and G is a finite group, then 1, the order of H divides G, the order of G, and the thing you get when you actually divide is exactly the index. Right, and recall that the index is the number of left, or you can also use right. They're going to be the same amount either way. Cosets of H in G. Okay. So this is useful. We're going to see it a lot from here on out. So this first one was just pretty basic, just kind of a direct application of this. So if I just hand you a group and I say, you know, this has order 48, and then I hand you a subgroup of it, what do you know about the order of this subgroup? What are the possible orders? This is what, 517. Oh, shoot. I didn't change the stream title. My bad, Nick. That would be something I can do. Sometimes I forget things. I just came from my friend's thesis defense, so I kind of prep for class very quickly. There we go. Can someone tell me what the possible orders are here? This should, I'm pretty sure everyone is very capable of this. Is anyone alive? Anything that divides 48? You gonna make me do the list? Fair enough. Alright, so we've got what? 1, 2, 3, 4, 6, 8, 12, 16, 24, 48. Fair enough. Alright, thank you, Ty. Yeah. Okay, so right, this doesn't tell us a whole bunch, but when we have a smaller group or we have more information, we can say a lot more. But first we should verify whether we necessarily could get all of these, right? So Lagrange's theorem tells you that the order of H is going to divide G. Question is it true that if some number divides the order of G, is there going to be a subgroup of that order, right? So let's just say if K divides the order of G, must there exist a subgroup H of order K? So, I mean, I told you in the book, no. What examples did you come up with? So you should give me a G and then say like why, maybe just because we've already found the subgroups, or some other argument for why it does not have a subgroup of a certain divisor of its order. So we've definitely seen an example in class before, we just haven't, pointed it out in this context. No subgroup of order 12 in S4. Okay. Alright, so yes, you're using the things that we prove in 2 problems. Okay, was there, if I hadn't given you that problem, could you have found anything? So yeah, I agree. S4, no order 8 or 12. Or 6 actually even. Is there anything else? So think about the other common groups we've dealt with in class, right? We've had like dihedral groups, we've had the quaternions, the Klein 4. Thoughts? These are subgroups, not cyclic subgroups. Oh, sorry. Yes, it does have that. It doesn't have order 8 cyclic. Yes, thank you. Right, it does have order 12. It does not have the... Does it have an order 6? Yeah, it does. Right. So, right. No cyclic subgroups. That's why it was later, yeah. Because we're about to make that statement. Order 6, 8, 12. But yes, A4 is a normal subgroup of S4, right? Of order 12. We've seen one though. So think about subgroup lattices that we've seen. So, think about like our dihedral, we've seen like D3 and D4 are the ones we've mostly looked at, but like D3 has the order 3 guy, right, with R, and it's got, 3 reflections of order 2. So that's not going to do it. D4, similar, right? You're going to have the 4 for your R, you're going to have some with 2. So maybe not these guys. But what about Q8? What about your quaternions? What are you going to end up with? Well, that also is rough. So this is actually a hard problem. So this guy, right, has your boom. So these guys are all hard. This was supposed to be, by the way, a challenging one. So we have seen an example, but you just don't know it yet. So, Mark just mentioned A4 being order 12 inside S4. So it turns out, so this is hard for the things that we've done. So it turns out that A4 has no subgroup. Of order 6. Right, so Q8 does not work. Yeah, so neither of these works. Also, are you guys getting some buffering on your end? I haven't had this issue in a while, but I've had a little bit on one of my monitors. Is the stream working for you? Buffering a bit, yeah. Okay. It seems to be working better now for me. I mean, our internet on campus is good, so I don't know if Twitch is... okay, yeah, it seems like things are better. Okay. So, yeah, this was supposed to be challenging, mostly because, yes, we have seen a group, but we haven't really seen why this is true. So this is a challenging problem, and it basically boils down to, so I'm actually going to use this as a problem set problem mostly because it would probably take a little bit too much time in class, and I want to kind of walk you through it. So this will be kind of a scaffolded problem where you'll see what would have to be true if there was a subgroup of order 6. So this is something you would argue by contradiction, using some tools that we have or will develop later today. So basically, if you, hopefully today, we'll see. So if you have order half of your group, it's going to be a normal subgroup. And using that and what the possibilities are for your cycle lengths is going to allow you to figure this out. So That's something I want to like step you through in a problem set. But this is like your small example that is often used for the converse not being true for Lagrange's theorem. Okay, so A4. So this is another reason to define the alternating group, for us to have talked about it, because one, it's an example of simple groups, which again we don't really have the definition of yet, but it also gives you a converse to Lagrange's theorem. Okay. Hopefully you're not still buffering, Delmas. It seems smooth on my end now, at least. Okay. So we have, yeah, okay, never mind. So for 519, this is what you guys were getting at with the symmetric group example, right? So that there is no cyclic subgroup of that order, and that follows from this theorem. So if you have some element in your group, then the order of that element divides the order of G. And the idea here, right, is just that, well, we have two definitions of order. The one that's most useful here, right, is the one actually relevant to subgroups, so that we can use Lagrange's theorem. So use the fact that the order of A is the order of the subgroup generated by A. Well, subgroup generated by A, as given by its name, is indeed a subgroup of G. So its order divides the order of G by Lagrange's theorem. And therefore, the order of your element, which is the same thing, also divides the order of your group. So why is this useful? Yeah, so now you can look at cyclic subgroups inside. So this is another one where like the dihedral group is somewhat interesting as well when you look at its cyclic subgroups, because all of the reflections, right, generate an order 2 subgroup, and then all of your rotations, well, you're going to get certain divisors. You can see like some pretty interesting things and like pretty quickly see what all of the subgroups look like and what their orders look like. S4 or Sn in general is interesting because you know the orders of elements via their cycle structure, right? So written as a product of disjoint cycles, we know how to determine their order. So for 520, our goal was to show S4 has no cyclic subgroup of order 8. And yes, this would also follow for 6 or 12 by this same argument. So what did you guys think for this? So again, my hint was write some sigma as a product of disjoint cycles. Why does this help? Any ideas here? I'll have to reset my Wi-Fi. Okay. So why is the disjoint cycle decomposition like relevant at all to order? Own inverses. Not necessarily. So transpositions, that would be true, but disjoint cycles, not necessarily. So like 1, 2, 3, 4, for instance, is it's just one disjoint cycle, and this guy is not its own inverse. So this is order 4. So you're thinking specifically of things like this. But so like if I write as a product of disjoint cycles, what is the order of sigma if I can write it like this? Is the least common multiple. Yeah. So this is the least common multiple of the orders of the cycles. Well, what are the possible lengths of our cycles in S4? We're pretty limited, right? You can either have a 4 cycle. So I guess here, possibilities. So yeah, you have a 4 cycle, like 1, 2, 3, 4 above, and that's going to be order 4. It's going to be easier if I just do order up here and write a number. You can have a 3 cycle and a 1 cycle, right? Which we usually omit the 1 cycle, but this is what would be going on, something like this, right? So you could have like a 3 cycle and then a 1 cycle. Well, that's going to be order 3 because we know the length of cycles themselves is just the length of the cycle. You can have a 2 cycle and 2 1 cycles, so something like this, right? A transposition by itself. That's order 2. You can have all 1 cycles, aka the identity, which is order 1. Are we missing any possibilities here? Is there anything else that I could get in terms of writing as a product of disjoint cycles? So we can do like 4 as 1 cycle, 3 and 1, 2, 1, 1, 1, 1, 1, 1. Is there anything else? There should be one more. Yeah, 2 disjoint 2 cycles. Right, so something like 1, 2, 3, 4. And in this case, right, this is the only one where you really had to do an LCM at all. You have 2 things, but the LCM of 2 and 2 is 2. Well, we see that the maximal order of a single element in S4 can be 4. Okay? And so, right, this is why I said you also can rule out 6 and 12 as divisors of 24 for orders of cyclic subgroups, or the order of an element. But we can get 12 with the alternating group. So, yeah, this is interesting. And you can do this in general, right? So like you could do this in S5 as well and just kind of run through your possibilities, but there you're going to have a few more, right? Because there you can actually get things like 3 and 2, right? You can have a 3 cycle and a 2 cycle, and you can get order 6 and stuff, and that's the max you're going to be able to do there. And so you can kind of do this ruling things out just by kind of exhaustion. And thinking about what is possible in terms of these cycle decompositions. And it's not bad if you have fairly small numbers, but if I ask you, in like S81, what's the maximal possible order, then that's going to be a pain. So not very useful past a certain number, but S4, S5, S6, like it's not too bad at all. Okay. Alrighty. So the next problem was essentially something we've talked about before, starting with a problem set problem a long time ago, but it was that if the order of G is prime, then G is isomorphic to ZP. So we had this back in the context of just what possible subgroups are there, and we said it had to be cyclic. We didn't say it had to be prime order necessarily, and we didn't have ZP defined at the time. But what's the argument here? So we've got, I guess I should say P is prime. Usually if I'm using P, I'm going to mean a prime number. But if we have a prime order group, why must it be isomorphic to ZP? And why is it in this section of our book? No possible proper subgroups because only divisors of P are 1 in P. Yeah, exactly, right? So if H is a subgroup of G, then the order of H is 1 or it's P by Lagrange, right? Has to divide P, P is prime, so it's either 1 or P. So thus, G is cyclic. Because if any non-trivial element, any G in G is not the identity, then its cyclic subgroup is equal to the whole group, because we know its order is not 1. Alright, so it must be cyclic, it's cyclic of order P, and we know all cyclic groups of order P are isomorphic to ZP. So I don't remember exactly what number that theorem was, but that was right. We had that classification where if you're infinite cyclic, then you're isomorphic to Z. If you're finite cyclic, then you're isomorphic to Zn if you are order n. Okay, yeah, exactly. Lagrange says no normal subgroup, non-trivial normal subgroups. Or maybe you meant non-trivial there, since we haven't defined normal yet. Okay, so the last thing I wanted to talk about is just like a couple examples with index, just to get used to it. We haven't talked about it that much outside of the proof of Lagrange's theorem, and also getting a little more used to the alternating group. So I did notice when looking through things that not everyone was sure exactly on the order of this subgroup inside S4. So this is subgroup of S4. It's generated by 2 disjoint 2 cycles. And there's not really like a real trick to this. You just kind of have to do their product and see like what you can get. So first of all, each element here, we know its order because we know how to do the order of elements in S4 or Sn in general, right? Again, it's the LCM. So these are each order 2. So we know that just multiplying by themselves, that doesn't get us anything new. So what are the elements of this subgroup? Well, we have E. We have 1, 2, 3, 4. We have 1, 3, 2, 4. And then we need to figure out, like, what is their product, and then, you know, what order does that have, right? So how many elements did you find total in this group? What is their product? Yeah, the product is 1, 4, 2, 3. And so you get another product of disjoint 2 cycles, and so this is also order 2, and so basically you just don't get anything more. And so what common group is this isomorphic to, by the way? Can anyone see what familiar group we have that this behaves exactly like? Yeah, it's V4, right? We have 3 elements of order 2, and then our identity. And, this is like your V, your H, and your VH if you want. Awesome. So when you're looking at the index, right, like you don't need to actually go through and figure out all of the cosets and like compute them by hand and do all this nasty work. You can use Lagrange's theorem, right? So we know that this should be the order of A4 over the order of H. I guess it's important here, right? We should verify that this is, it's clearly a subgroup of H4, or of S4. H is a subgroup of S4, but H is also a subgroup of A4. So this makes sense to talk about because these are all even permutations, right? E is even, can be written as 0 transpositions, or 2 if you want to just do the same one back to back. Yeah, you would have to, but you can. Yeah, they ostensibly did this beforehand, so yes, you do have to do that. Yeah, and so these are all even, and so this really is a subgroup of A4, right? We can't just in general say like, oh, I've got some subgroup, it's also a subgroup of this if its order is like less than half of the group or something. You should check that like these are really even permutations. So, all even. And so then we can use Lagrange there and just get, 12 divided by 4, and so there will be 3 cosets of H inside A4, and for S4, we're going to get 24 over 4, or 6 cosets. Okay. So questions on index, Lagrange's theorem, anything that we've done before we start talking about normal subgroups. So normal subgroups are super important, and they're going to allow us to move on to quotient groups later on, which will be just like a new kind of group that we haven't seen yet, a new construction. But any questions before we kind of switch gears a little bit? We're still going to be talking about cosets. Okay, all right. In that case, let us talk about normal subgroups. So we had the question earlier, right? Like, if G is abelian, we notice that all of our cosets, right? Again, H is a subgroup of G. Then this was true for all A and G, right? We got the same left cosets and right cosets because, order doesn't matter in an abelian group. So your first question to ask would be like, is the converse true, right? Like, is this an if and only if statement? Does this only happen for abelian groups? But we know that answer too. So this isn't true just for abelian. Well, sorry. That's the case, but like we also saw, we did see that. Like with Q8 is an example. So for Q8, this is true as well. And Q8 obviously is not abelian. so I mean, we didn't technically run through all of them. You showed that, you know, AI equals IA, and that a -1 equals -1A for all A in Q8. But you might imagine that all of the I, J, and K arguments are going to look exactly the same. So this is true for Q8. All of the subgroups, all of the left cosets are equal to the right cosets, no matter which subgroup you choose. And we've even seen that with D3 for a certain H, right? So this is true for like all H here in Q8. In D3, we saw that for R it was true. But it was not true. So, you know, you have enough examples, you might say, like, is this always true? Well, it's not always true, because we saw that, for instance, RS is not equal to SR. And so it's not always true. Sometimes we will have left cosets not equal to the right cosets. So then, you know, the natural question to ask is, well, when is it true, right? It's true for abelian, it's true for some non-abelian, but not all non-abelian. So, you know, what is the correct thing? And so we have a name for these things, and these are called normal subgroups. Okay, so this definition kind of comes from that question. These are actually very interesting objects of study inside our groups. So H is a normal subgroup of G. And, you know, normally we write H less than or equal to for a subgroup. If it's a normal subgroup, we do this like triangle kind of on its side there, if you're used to having a base that's flat. This would be the notation, so denoted H is normal in G, like this. So we're going to see several equivalent formulations, but just the definition we're going to work with is if AH equals HA for all A and G. So we'll have a theorem soon that gives us kind of a different way to check this. Okay. So this is what it means to be normal. And so, you know, right away, so this is 527, we want an example of an H in G such that H is not normal in G. So we just saw one. It's H equals subgroup generated by S in D3. Right, and that was a problem we did at the very start of this chapter, right? So this is a non-normal subgroup, so definitely not everything is normal, but, you know, sometimes you do have a lot of normal subgroups, and if you're abelian, everything is normal. So what are things we always know are going to be normal, right, for any group? So say I hand you a non-abelian group, so you definitely can't say everything is. Are there things you always know will be? Well, you kind of get the same answer as subgroups, you know, because like not every group has non-trivial subgroups, or non-trivial proper subgroups. But you always have the subgroups like the trivial group and the group itself, right? And it turns out both of those guys are always normal in your group. So that's kind of a starting place. So this is 529 for us. So if G is a group, then the trivial group is normal in G, and G itself is normal in G. So I think this is a useful place to start because, well, they're very easy cases, but they do get you used to like how you might argue such a thing, right? So how do we prove this? Well, let's do the trivial group first. So again, what does it mean to be normal, right? We want to think about our goal. So we want that all of our left cosets are equal to our right coset. I guess I used A above, so I'll be consistent. Equal our right cosets for all A and G. Well, what are these cosets? They're very simple, right? You only have one thing you're multiplying by, and it's the identity. So your left coset is A, and your right coset is A. So we're done. All of your cosets are just the singleton subsets of the elements of your group. Okay, so it's pretty straightforward. Okay, and then what about G being normal in G? Well, here we're looking at the left coset A times G, right, the whole set. What do we get if we multiply a little a by the whole group G? What is this coset equal to? Right, it's going to be some subset of your group. What subset of your group is it? Any thoughts? Remember that G is a group. This is left multiplying your group by some element. We know things about left multiplication as a map. It's always an isomorphism. It is the whole group itself. Yeah, exactly. And right multiplication is also, right, like this is an invertible thing. You left multiply by A, right? So like if you want to explicitly see this, right, so if you have x in AG, then x looks like A times little g. But if you want to show that x, well, then x is in G, right? So that's subset this way. And then if you want to see this way, just take something in G. So take x in G, or let's just call it y instead. Let's take some y in G. Well, then y can be written as A times something in G by just doing A times A inverse y, which is in AG. Right, so those are equal, right? It's an invertible map. And so the same reason it's also equal to the right cosets here. So these are just both equal to the whole group. And so this is also a normal subgroup. And it may be useful to think about what the indices are in these cases. So in general, the index of the trivial group inside G, well, we saw what are the cosets. The cosets are just all of the singleton sets for every element in my group. So this is just going to be the number of elements in G, right? Because you get one coset for each element. And then how many cosets did we have for G inside G? Well, we only got one, right? All of the cosets were equal to the group itself. So you get one. So this is always true. And notice that like the order of G could be infinite, you know, so like the order of, or the index of 0, for instance, inside Z is infinite because there are infinitely many numbers in the integers. But yeah, this is always true. Index makes sense for infinite groups, it makes sense for finite groups. So yeah. Alrighty. So another little statement we can make, this is something we already proved before in 5.8, right? We said if G is abelian, I mean, we've already talked about this out loud, but I just want to cite it explicitly, right? So if G is abelian and H is a subgroup of G, then AH equals HA for all A and G. And so what we can conclude here is that H is normal in G for any subgroup of G if G is abelian. So any subgroup of an abelian group is normal. So that's an important thing to remember. So I'll just say important. Important thing to know. Okay. All right. So we had another example, right? So this is just translating into the new terminology, right? So we have seen before as well. But we'll have a quicker argument here shortly. Before that, all subgroups of Q8 are normal. And I think that was, where did that come from? 5.4. Most of the work done in 5.4. Right, so you already looked at subgroup generated by I, subgroup generated by -1, and now this previous result, right, about the identity in the whole group tells you that 1 and Q8 itself are going to do the trick, and then the last things to check would be the subgroups generated by J and K, but those arguments are like exactly the same, or very similar to that for the subgroup generated by I. So it would just be kind of repeating the same process there. So something else that we've kind of noticed, so we have a few examples here, so let's think about this. And I'll do specifically subgroups that are, or subgroups of groups that are not abelian. So A4 is normal in S4. I, J, K, all their cyclic subgroups are normal in Q8. We saw that the left and right cosets were the same for the subgroup generated by R in D3. What do all of these have in common? Think about the orders of these subgroups with respect to your whole group. What do they have in common? So like this is order 3, this is order 6. These are order 4, this is order 8. This is order 12, this is order 24. They're not all cyclic, so the last 4 are, but the alternating group is not cyclic. But the orders, what are we noticing here? They're all half of your group. So this is actually something that is always true. So yeah, not necessarily even, right? Because this is order 3. It's very much the being half part. So in all of these cases, if you let these guys be your H, then remember that the index from Lagrange's theorem, we can also think of this as the order of the group over the order of the subgroup. And so in these cases, our index is exactly 2 for all of these. And all of them were normal. Well, this pattern actually always holds. Okay, so this is, I don't know if I've been doing 5, but yeah, 532. So this will be kind of what we close with here. But this is another very important result in terms of finding something that is always normal. So if you have a subgroup that has the order half of your group, in other words, if you have a subgroup with index 2, so let G be a group, and H a subgroup of G with index 2. So this is a more general statement, by the way. Like I want to point out, maybe you'd say, Dr. Gates, why are you not just saying that the order of H is half of the order of G? This works for infinite groups too. Right? Because I can always talk about index. It's just the number of cosets. And so, this is, I guess I should specify up here, right? This is if G is finite, right? That's the only time that Lagrange's theorem is going to apply there. And so, this is something more general. So if you have an infinite group, like, GLN or something like that, right? Group of matrices, then that guy is not abelian. And so you still might ask yourself about normal subgroups, though. And so then, if you can find a subgroup of index 2 there, then you could conclude that H is normal in G. Right? And you can still talk about cosets for infinite groups and thus talk about index. So why is this true? Well, the key here is very much that there are two options, right? So like with A4 and S4, you had like your odd permutations, your even permutations. With D3 and R, you basically had your rotations and your reflections. And so like you had this dichotomy where you were just one or the other inside these groups. And, it's not necessarily that clear or that nice of an explanation in general, like even versus odd, but either way, there are only two, so there's only so much wiggle room you have. So again, we want AH equals HA for all A and G, and we have only two cosets, H, and then, say GH where G is not in H. And two left cosets and two right cosets. But again, H is a coset of each, and then maybe I'll call this HG prime or something. How do you divide infinity by something to get to? You don't. So again, like Lagrange's theorem does not apply there. This is for finite groups. So you're not dividing. It's using the definition of index as the number of cosets. So this is something that is true for finite groups by Lagrange's theorem, but it's not the definition. The index is the number of cosets. Because that's a good point. You don't. Yeah. Dividing by infinity is a strange thing, for sure. Okay. So, well, if I want to show this, I'm just going to show both directions. Right? So, if x is in AH, I'm going to show that it's in HA. Right? So, I have a couple of cases, right? Because I don't really have much that can happen here. So, like, what can happen? Well, either x is in H or x is in GH, right? So either x is in H or x is in GH, i.e. x is not in H. Right? You're either in H or you're not in H, and those are your two cosets. Well, if x is in H, then by our theorem 514 says XH, what am I doing? X, which is equal to A times little h, is in H. So A equals XH inverse is in H because H is closed and has inverses. And if A is in H, then AH equals H. And that is also equal to HA. So that's a direct application of 514. If you're in the subgroup generated by H, or subgroup generated by H, the subgroup H, then you have this closure argument, and so you're equal to this. And so we started in AH, and we ended up in HA. If X is not in H, then, well, x being an AH, first of all, means that this is true. Then since XH equals AH, and X is not an H, we have XH not equal to H, so AH is not equal to H. And remember, these are disjoint, right? And so which right cosets did we have? So if AH is not equal to H, then it has to be the other right coset. So it has to be this one. Right? It has to be HA. There's no other option. And so I will let you try to show the other direction. It's very, very similar, but I want to see if this makes sense, and then maybe we can talk about it next time since we're a little over time now. And we can either start class by just starting this from the top again, or if it seems like everyone gets it, then we'll just kind of do the back half and move forward. Okay. Don't forget test corrections if you want to do them by the end of the day. If you have questions on those, I can answer them. I mean, I may not give you all the details, but I can give you a little nudge on some things if you're still really stuck, despite my little hints on what I gave you back. So yeah, just let me know. All right, have a good weekend.